Welcome back to Probability and Statistics. We are in our fourth installment of 10, working through the book Elementary Statistics, fourth edition by William Navidi. In this lesson, we're going to take a look at Chapter 6. Chapter 6 has three sections in it, but I'm only going to be covering two of them, sections 1 and 2. So if you are curious to know what's in section 3, I encourage you to crack open the book and take a look. So in this lesson, we're going to be looking from section 1 at random variables. What are they? How do they operate in this context of statistics? And then in section 2, looking at what's called the binomial distribution. I also have in parentheses geometric distribution. That is because though it's not covered in these series of lessons, it's very, very closely tied to the binomial distribution. So I just want to make some mention of it at the end of the lesson, just more for awareness sake. So let's go ahead and get going. We are going to be taking a look at, like I said, random variables out of section 1. I'm going to give you some definitions to start. We'll do a couple examples and then move forward with some other ideas. So when we talk about a random variable is a numerical outcome. So numerical outcome that is a number of a probability experiment. So numerical outcome of a probability experiment. If you recall it, a probability experiment is just exactly that. It's doing a trial over and over and over again. And as we do that thing more and more and more, we come to the, closer to the true probability of whatever that situation is. So if I'm wondering what is the actual probability of getting heads when I flip a coin, I flip it a bunch of times. I might, get 100%, then 66%, and then, slowly get closer and closer to 50%. So that's all we mean by a random variable. It's just an outcome that represents, or a numerical outcome that represents something that we're looking at in the experiment, an outcome that we want or are desiring. Oftentimes, when we talk about random variables, they are usually denoted with capital letters. So just like in algebra, for example, we introduce letters and use those in equations and such. Oftentimes those are lowercase. In this case, they are capital. And that's just to distinguish them as a random variable in this type of a context. So there are two types of random variables. There's what's called a discrete random variable and a continuous random variable. And if you know those words discrete and continuous from mathematics, this is going to make complete sense to you. When we talk about discrete, we're talking about values that if I were to take two consecutive values in the list, in the data set, there would not be another value between them. So oftentimes we're talking about whole numbers here. So I'm going to say it this way, that discrete random variables are possible values that can be listed. So whole numbers, for example, would be a good example of this. Because if my data set is whole numbers, and I pick, for example, 2 and 3, I can't pick another value between those. So my set is going to be something like 1, 2, 3, 4, 5, and so on. No decimals, no fractions, no possibility of that. That would be the idea of a discrete random variable. On the other hand, a continuous random variable can take on any value. So it can take on any value in an interval. So again, going back to my example of having taken 2 and 3, in a continuous situation, if I'm looking at the interval from 2 to 3, I could pick another number like 2.5. And now if I look from 2.5 to 3, I could pick another number like 2.7. And between 2.5 and 2.7, I could pick 2.6, and then 2.65 and 2.653, right? And I can keep going forever and ever and ever, because I can just keep adding decimals and being more and more and more specific or precise, and never, ever, ever come to a place where I've run out of numbers between two numbers. So that's the difference between a discrete and continuous value and how that relates then to this idea of random variables. So if you think back to the last lesson, we did some work with probability. We looked at flipping coins and rolling dice and things like that. Those were actually situations where we were dealing with a discrete random variable. We just didn't define it in that way, nor did we formalize it in that way. And so that's what we're going to do right now. We're going to take a look at an example, and we're going to come back to this idea of tossing coins, because why not? And so we're going to toss a coin 3 times. The difference now, though, is that we are going to specifically define a variable within the context of this problem. And then it says find the probability distribution of X, of that random variable. So while in essence, it is very, very similar to what we did in the previous lesson, you're going to see some differences because of how we now define this random variable and what it means in the context of the problem. Okay, so this X, this is our random variable, and specifically in this case, a discrete random variable, because if you notice, it says that X is going to be the number of heads. Well, you can't have a fractional number of heads. You can only have no heads or 1 head or 2 head or 3 heads, right? So it's a discrete, specifically a discrete random variable. All right, so I'm going to start like we did in the previous lesson. I'm going to list out the sample space. I'm going to list out all the possible outcomes. So for example, flipping 3 coins, I could get 3 heads. I could get head, head, tail, head, tail, head, tail. Oops, I missed one in there. I could get head. All right, I'm gonna start this over because I'm gonna get myself really confused if I don't stick to a certain pattern here. Let's do 2 heads. So we have heads, tails, heads, and then tails, heads, heads. So that takes care of all the ways we can get 2 heads. Now let's go 2 tails. So we can get tails, tails, heads, tails, heads, tails, and heads, tails, tails, and then finally tails, tails, tails. Wow, that was more difficult than it should have been. But we should have 8 outcomes there. And so again, thinking about what we've done previously, that would be our sample space. And if I wanted to turn that into a probability distribution, I would simply list the probability of each of those occurring. In this case, each one has a 1/8 probability. So in a probability distribution, I would just simply write 1/8 under each of those. But in this case, that's not what we're doing, because now we've defined a variable and we've said that X is the number of heads that we get when we flip a coin 3 times. So X could be 0, no heads. It could be 1, 2, or 3. And in a probability distribution, we still want to have a probability assigned to each of those. But what we're going to do now is from that list, we're basically just finding the probability of all the different outcomes that exist. So for example, there's one way to get no heads, and that's getting the 3 tails. So the probability is 1 out of 8 when X is 0, or 0.125. For 1 head, there are 3 ways we can get 1 head. So that has a 3/8 probability, or 0.375. 2 heads, same thing. There's 3 different ways. So 3/8, or 0.375. And then just one way to get 3 heads. So we're back to 1/8, or 0.125. Okay, so a little bit different than what we saw previously, but again, same idea. Our check here to make sure that we did it correctly is if you add up all your probabilities, again, it should equal 1 or 100% of everything that could happen when I flip a coin 3 times. Now, just like we've done before, I could find the probability now of certain things. So if I want to find, for example, the probability of getting 2 heads, what I'd really do is I'd be saying this: the probability of X equals 2, right? Because I'm saying X is the number of heads. I want the number of heads to be 2. So probability of getting 2 heads would be 3 out of 8, or 0.375. If I want the probability of at least 2 heads, I could write that out in words: at least 2 heads, or I could just say X greater than or equal to 2. And in that case, I'm adding up 2 and 3. So I'm taking 3/8 plus 1/8 is 4/8, or 1/2. Okay, so just so you can start to see some of the symbols and ways that we write this symbolically. Okay, let's do another example. This is an example that we're going to start, and we'll do a couple things with it And then I'm going to give some more definitions, and we're going to come back to this example and do a little bit more with it then. So in this example, it says that a stadium sells tickets to its sporting events in 4 tiers. The stadium has 40,000 seats. Tier 1 has 9,000 seats that cost $55 each, or $55 per ticket. Tier 2 has 11,000 seats that cost $42 each. Tier 3 has 13,000 seats that cost $30 each. And Tier 4 has 7,000 seats that cost $18 each. Let X be the price for a randomly selected ticket and find the probability distribution. So again, we're defining X to be price for a single ticket. And so what we want to do is we want to look at basically what is the probability that if I randomly selected a ticket from the 40,000 seats that are available, what is the probability that it comes from one of those 4 tiers? What is the probability that it comes from tier 1, from tier 2, from tier 3, from tier 4? And then what we'll do is we'll use that probability then and attach it to the cost. Okay, so here's how it looks. I'm going to find the probability of randomly picking a ticket from tier 1. So tier 1 has 9,000 seats. There are 40,000 total in the stadium. So if I take 9,000 divided by 40, randomly picking a ticket, there's a 0.225 or 22.5% probability that that ticket would be from tier 1. Now I'm going to do the same thing for the other tiers, tiers 2, 3, and 4. So tier 2, there are 11,000 seats divided by 40,000. That's going to give us a probability of 0.275. Tier 3 has 13,000 seats, and that gives us a probability of 0.325. And then finally, tier 4 has 7,000 seats, and that gives us a probability of 0.175. So again, if you add those together, you should get 1 because it represents every possible outcome of randomly drawing a ticket for seating in that stadium. So now that we have those probabilities, remember, it says find the probability of distribution of X, and X is the price for a randomly selected ticket. So what we found really are the probabilities. Our table then that we're going to create, X is just the actual price of each of those tickets. So I'm going to actually do this backwards because I always like to put the smallest numbers first. So tier 4, for example, those tickets are $18 each. Tier 3 costs $30 each. Tier 2 are $42, and tier 1 are $55. So I'm going to just do that backward. So I'm going to start with $18 here, and then $32, $42, and $55. Okay, so again, just those prices per seat. The probability then of getting an $18 seat, well, those are just tier 4 seats. So it's whether I say what is the probability of getting an $18 seat or the probability of getting a tier 4 seat, they mean the same thing. So for P of X, I can just transfer down those probabilities. So this is 0.175, 0.325. Notice we're going backward here, 0.275, and 0.225. Okay, so that would be my probability distribution. Okay, the next part of it now says construct a probability histogram for the probability distribution. So what we are going to do is just simply take those 4 categories and make it into a histogram with 4 bars. So we've got our X and Y axes, our horizontal and vertical axes. This is going to be our probability on this side, or P of X. And this is going to be our ticket price in dollars, or X. Okay. All right. So we have, look at our probabilities. Our probabilities only go up to 0.325. So I really only need to go up to about 4 on my scale. I don't need to go real high. What's called this 1, 2, 3, 4, 0.1, 0.2, 0.3, 0.4. And then our ticket prices. What I'm going to do here, because this is discrete. Now think about a histogram. A histogram normally would have a range of values. So I might go from 0 to 5, 5 to 10, 10 to 15. But because this is discrete, we're only using the four values, 18, 32, 42, and 55. And I don't want to in any way, shape, or form denote this idea that it's continuous, that we're using values between those ticket prices. So what I'm going to do is I'm going to just simply label my axes with those ticket prices. And when I create my histogram, I'm going to draw bars that just basically show that they're at 18, 32, and so on. So 18 goes up to 0.175, so about to maybe here. So I'm just going to, let me put this a little more centered. I'm going to just go from here to here. And that's going to be our bar for tier 4. And then tier 3 goes to 0.325, so quite a bit higher up. So I'm just going to do this and this and this. Tier 3, or excuse me, tier 2 is 0.275. So maybe about right here. And then tier 1 is 0.225. So maybe about right here. Okay. So that's how we can make a probability histogram from that data and from that information. Okay, let's come back to some more definitions here. Like I said, after these definitions, we're going to come back to the stadium problem and do a little more work with that based on these definitions. So we've got the definition of mean of a discrete random variable. Another way you might see this said, this idea of a mean of a discrete random variable, is expected value, or symbolically E of x. Okay. So expected value is exactly that. When you think about mean, right, we're thinking about on average what kind of test scores, what kinds of weights or heights, things like that would we expect to see expected value. All right. So when we talk about the mean of a discrete random variable, it is the sum of the products of each value. So these are, when I say each value, I mean our x values, and its corresponding probability. So the idea here is that I'm going to take, like, for example, and we'll do this in just a minute more formally, but I'm just simply going to multiply those columns. I'll take 18 times 0.175, 32 times 0.325, and so on. That's taking the product of each value and its corresponding probability, and then the sum, just adding those all together. So another way to write this, we could write that the mean of x is the sum of x times p of x. Okay, and maybe put a little I on these just to denote that they do change, obviously, because you have more than one x value in a probability situation like this. All right, next one, interpreting the mean. So once you have that value, what does that mean? So what are we saying? And basically, it's like any other mean. It just says that if a probability experiment is repeated many times, talked about that before in this lesson and in previous lessons. Let me rewrite that a little bit cleaner. In many times, the average of all the values produced, the average of all the values produced will approach the mean of the random variable. The mean of the random variable. Okay, so again, so I'm just reading it all at once. So if a probability experiment is repeated many times, the average of all the values produced will approach the mean of the random variable. Now, this is how we interpret it. So once you have the value, this is really just kind of how we would state what it means. So if a probability experiment is repeated many times, the average of will approach the mean. And so like in this case, we want to specify what is that mean, okay? But that's kind of how we would state in words what that mean actually is or means. All right, and the law of large numbers for means, we looked at the law of large numbers before. And so here in this context, it just means that the larger the sample size, the larger the sample size, the closer the sample mean will be to the population mean. The sample mean will be to the population mean. Okay. And so again, just that idea that obviously the more, ideally we would get the population. I would sample, using that word loosely here, the entire population. I would get data from the entire population because I would know then exactly what the population is. Again, very, very unlikely to happen in most situations. So we sample a smaller size, but I still want that sample to be as large as possible because the larger it is, the closer my predictions are to what the population would actually be. So let's take a look at one more definition and then we'll get back to our stadium example. And so this is the definition of variance and standard deviation of a discrete random variable. So we've talked about variance and standard deviation before. And in this case, when we think about variance for a random variable, variance is, again, just really standard deviation squared. And in this case, what it is, it's the sum. I'm gonna give this symbolically, and I'll kind of explain it, but it's the sum of the difference of the value and the mean squared. So this should actually sound very familiar because it's very, very familiar to what we did when we found variance before for just a data set. We found the mean, we took a value minus the mean and squared it. We took the next value minus the mean and we squared it. And we added all those together, if you remember doing that in a previous lesson. But in this case, these differences are weighted based on their probability. So we don't just simply stop here squaring the numbers and adding them together. What we're going to do is before we add them all together, we are going to multiply each of those squared differences by the probability. And then we'll add everything together, and that gives us the variance. So let me kind of walk through this one more time and kind of just in words, write out in words, kind of symbolically, what these symbols mean as we walk through it. So this is really the sum of the difference of value and mean squared. That's mean. I rewrite that. Mean squared. Okay, so sum of, and then the difference of the value of the mean squared times the probability. And because of those brackets, we'll do this part first, right? We're going to take the difference of the value and mean squared times the probability, go to the next value. Difference of the value and the mean squared times its probability, go to the next value, continue that, add all of those up. That's our variance. And then recall that standard deviation, which I'm just going to abbreviate SD here, standard deviation is just the square root of the variance. So once you have the variance, you can take the square root to get standard deviation. All right. So coming back to our stadium example, then this is our probability distribution that we created earlier. And we're going to just find now the mean and the standard deviation. So the couple of definitions that we just went through. So I'm going to do this by hand, but again, certainly there are technologies and such that can do this more efficiently, even from the standpoint of setting up a formula in Excel, for example, and then just kind of copying it for each value. So you don't have to keep doing this over and over again. But let's take the mean of X here. So the mean of X, again, is just really multiplying each of those columns and adding it all together. So we're going to take 18 times 0.175 plus 32 times 0.325 plus 42 times 0.275 and plus 55 times 0.225. Right? So that's all it is. Just multiply those together, add them all together, and that's going to give us our mean. In this case, our mean is $37.48. And so again, it says interpret. So all this means is as more tickets are sold, the mean price of tickets sold approaches $37.48. In other words, if the stadium sold every single seat, all 40,000 seats, they would earn an average of $37.48 for each seat sold. Okay. So that's kind of all that means. All right. Now let's just find the standard deviation of the probability distribution. So again, what we're going to do now is we've got the mean. The mean is 37.48. So we go through each value, starting with 18. We're going to take 18 minus 37.48. We're going to square that. But again, we also want to multiply that by its corresponding probability, 0.175. And then we'll do the same with 32. Square it, multiply it by its probability, and so on. I'm not going to write all four of them out. You get the idea. And then once you've got all four, then we add them together. And our variance in this case would be 150.849. Okay. And then standard deviation is just the square root of that, which in this case is 12.28. All right. And if you remember the interpretation for standard deviation, we're basically saying that tickets, or ticket prices, I should say, ticket prices typically vary by $12.28 from the mean of $37.48. So that's all standard deviation means. Again, it just means typically how far away would we find prices at this stadium from that mean of 37.48. Okay, let's do one final example here, and then we'll get into the binomial distribution. So here now, we're going to look at a life insurance situation. I find this fascinating. Now, understand that this is a very, very simplified problem. If we were to actually do something of this effect in the true life insurance world, we'd have much more complicated formulas and factors that we'd be looking at and things like that. So this is just a very, very simplified version, but gives us an idea of what life insurance companies are thinking about when they set those premiums for their policies. So it says the annual premium for a 1-year, $100,000 term life policy for a 60-year-old man is $1,480. So you're going to pay $1,480 for the year as a 60-year-old man to basically be covered for $100,000 for the next 365 days. The probability of the man living after 1 year is 98.7%. Okay. Let X be the profit made by the insurance company. Okay, so we've got our random variable. It's the profit that the company is going to make. And it says find the probability distribution of X. Okay, so think about what's happening here. Let's say that I'm the 60-year-old man, and I'm going to go out and I'm going to buy this policy. Okay. Now, I don't mean for this to get morbid, and if in all seriousness, if you've had a loss in your life recently, and that's difficult for you right now, you may want to actually just skip this because this is truly about death and benefits. But the idea here is I'm that 60-year-old man, and we're looking at this through the eyes though of the insurance company and what they would make depending on what happens to me. Okay. I paid $1,480 for this policy. So if I live to the end of that year when the policy expires, they are going to make $1,480 because they got my premium that I paid and they didn't have to pay anything out on my behalf. I'm going to actually put that in the second column. So that would be their profit. It's a positive because it's a profit. They made money. Now, if I die during that 1 year period, they have to pay me or my family, my benefactors, $100,000. So if we take $100,000 minus, or excuse me, I should do it the other way. They got the 1480 from me, but then they have to pay out $100,000. So they are going to lose $98,520. So those are the two kind of possible outcomes here. I live and the company makes 1,480, or I die and they lose 98,520. It tells us that the probability of living after 1 year for a 60-year-old man is 98.7. So in other words, the probability that the insurance company will make the $1,480 is 0.987, which means that there's a 1.3% probability that I will die and they will have to pay out. So this is going to be 0.013. Again, if we add those two probabilities together, they add up to 1 because we've covered 100% of the outcomes that are possible here. Okay, so that's our probability distribution. All right, so now we're going to find and interpret the expected value or the mean of the profit. So again, expected value or mean is simply taking the value x times its corresponding probability, doing that for all the values and adding them together. So if I take negative 98,520 times 0.013 plus positive 1480 times 0.987, and that's going to give me $180 positive. So what that means is that for many policies sold, the company, the insurance company, can expect to profit $180 per policy on average. So per policy, and I'll throw on the on average there. Okay. So when you think about an insurance company, this is really what they're doing is they're doing a risk analysis, right? They're saying, what is the probability of this person buying our policy dying during the time of the period for that policy? And based on that, then they set their prices because obviously they want to make a profit. They need to make a profit in order to keep operating as a company. And so in this case, for example, it's not a very large profit, it's $180. But a lot of insurance companies also try to work on volume, right? Where they're selling thousands of these policies in all different shapes and sizes. Now, that may be a small profit margin. I don't know what a profit margin is for an insurance policy. But I really like that idea, but this example, because it just gives a little glimpse, right? And so you could add more factors to this as well, right? You could, and really what it comes down to is really these probabilities. So, for example, there might be a 98.7% probability of a 60-year-old man living through that 1 year. But if that person is a heavy smoker, that probability probably goes down. If they engage in high risk behaviors, skydiving and rock climbing and things like that, that probability is going to go down. And so based on all of those factors, they're going to adjust those probabilities, and then based on that, typically they pass on the cost to that individual and say, well, because you're a high risk, to us as a company, you're going to have to pay more for your policy. All right. Last one on this, and then, like I said, we'll switch over into the binomial distribution. So it says, what should the insurance company charge to break even on the policy? Okay. Well, there's a couple ways to think about this. The easiest way to think about this is the fact that they're going to have to pay out $100,000 if the person passes away during that year. And we know that the probability that they pass away is 0.013. So if you just take 100,000 times 0.013, the probability or the expected value for that outcome, for that individual outcome, is 1,300. So that's their break even point. If they charge $1,300 for the policies, if they sell many, many, many policies, they should expect to break even. Okay. Another way to think about this is we know that they profit $180, right? That we figured that out in Part B. That at 1480 they profit $180. Well, take away that profit. If it's 1480 a policy and we take out the profit, we get $1,300. Okay, so that's their break even point. Okay, let's move on. Let's finish up with the binomial distribution. And there's not actually going to be a lot here to say. I'm going to go through an example. We'll describe or define what the binomial distribution is, and then we'll finish up with one more example. So it says a basketball player makes, on average, 70% of her free throw attempts and misses 30%. Let X be the number of free throws made. Find the probability that the player makes 2 free throws out of 3 attempts. Okay, so pretty straightforward, right? So 70% chance that she's going to make it, 30% chance that she's going to miss it. We want to know the probability of her making 2 out of 3 attempts. Well, that's pretty straightforward. She's got a 70% chance of making 1. She's got a 70% chance of making 2, and she's got a 30% chance of missing, so that she made 2 out of the 3. And if we multiply those together, we get about 0.147, or about 14.7%. Long pause, because if you're looking at that number and really thinking about that number, you might be thinking, wait a minute, she's a 70% free throw shooter. She makes 70% of her shots. And you're telling me that she has less than 15% chance of making 2 out of 3? That doesn't seem right. It seems a little low. If you're thinking that, you're absolutely correct. The problem is when I multiply 0.7 times 0.7 times 0.3, I am assuming then that the outcome happens in that order, that she is going to make, and miss specifically in that order. But that's not the only way that she can make 2 out of her 3 free throws. She could make the first, miss the second, and make the third, or she could miss the first and make the next 2. So there's actually 3 possible ways. So because of those 3 ways, we need to multiply now by 3, and the actual probability is about 44%, 0.44. This is an example of a binomial situation, or a binomial distribution. So let's go ahead and let's define what those characteristics are for a binomial distribution, the conditions. So the first one is that there are 2 outcomes. And in statistics, we define those as success or failure. Now, success is not necessarily good. Failure is not necessarily bad. It's just simply how we classify one result versus the other, because there's only 2 things that can happen. In our case of the basketball shooter, the free throw shooter, she can only make or she can miss. There's no other possible outcome. And so there's 2 outcomes. Probably we're going to call a make a success and a miss a failure, but we could reverse it. There's no reason not to. When I flip a coin, there's only 2 outcomes. I either get a head or I get a tail. Is heads good or tails good? Is one a success and the other failure? That's just how we categorize. All right, the second condition is that we have independent trials. In other words, we don't want a situation where one trial is affecting the outcome of another. Okay, so when we talk about independent trials, one trial has no effect on the next. Effect, I'm not actually sure. So we could argue that if this person is in a game and she makes her first free throw, that gives her a little extra confidence to come back and make another one, that her probability would actually go up. Or on the flip side, if she bricks it, if she misses it, maybe her confidence level goes down, and she has a lower probability of making or missing the next one, or I should say making. Yeah. Bottom line is, we could argue that in that situation it changes, but I think for practical purposes of this, let's just assume that every time she steps to the line, she's got a 70% chance of making that specific free throw. All right, that would be an independent trial. All right, thirdly, the number of trials is fixed. Number of trials is fixed. So she's not going to just go up to the line and just keep shooting free throws until she gets tired of doing it, right? She's taking exactly 3 free throws, okay? We would just say then that there are n trials, okay? And then the fourth one is the probability of success. This is kind of tied to the second point, but the probability of success, whoops, I spelled that wrong. Let's try that again. Probability, I always get tired towards the end of these lessons and start making mistakes. Probability of success is the same for all trials. Now, it is possible to have what might seem like a binomial situation, but because of this, it's not. Let me give you an example of that. Take a multiple choice test, for example. Let's say you're going to do a 20-question multiple choice test. Now, when you take a multiple choice test, a lot of times you have, maybe 4 possible answers, A, B, C, or D. But if you think about it, there's not 4 outcomes. There's still only 2 outcomes. You're either going to get it correct or you're going to get it wrong. So in that case, like with 4 possible choices, you have, the success would be picking the right one. Failure would be picking one of the 3 incorrect. They're independent. How you answer one should have no impact or bearing on how you answer the next one, or whether you get one correct should have no bearing on whether or not you get the next one correct or not. The number of trials is fixed, right? We've got 20 multiple choice questions. That's fixed. In this case, then, if they're all 4, have 4 possible outcome or 4 possible choices, we would say that the probability is the same for all trials, right? You have a 25% chance of getting it right. You have a 75% chance of getting it wrong, assuming that you're simply guessing. So that would be a binomial distribution. But if I instead make 10 of the questions with 4 options and 10 of the questions with 5 options, so I do an A, B, C, D, and I do an A, B, C, D, E, the first 3 conditions still stand. 2 outcomes, right or wrong. Independent trials, one doesn't affect the other. Number of trials fixed, there's still 20 questions. But now the probability is different whether I have 4 options or 5 options. 25% chance of getting it right when there's 4, only 20% chance of getting it right when there's 5, again, assuming that I'm guessing. And so that last condition would fail in a situation like that. But those are the 4 conditions that must hold in order for a distribution to be considered binomial. So when we have a binomial distribution, if you want to find the probability, and we've seen something similar to this before when we talked about probability and we talked about combinations and permutations. This involves a combination. So it's a combination of n trials choosing x as our number of successes times p to the power of x times 1 minus p to the power of n minus x. Okay. Let me write the basketball problem in this form and make some comments about how this formula works and why it is what it is. So in our basketball problem, we would want, in fact, let me just do this just so we have reference here. So for basketball, we wanted basically the probability of x equals 2, right? We want 2 out of the 3. So that would be 3 trials, 3 shots, making 2. There's a 70% chance of making it, and she wants to make 2. There is a 30% chance of missing, and we expect that, or in this case, she's going to miss 1. Okay. Notice a couple things here. First of all, if you were to find 3 choose 2 or 3 combination 2, use Excel, use a calculator. I'll mention, I'll just do this now. In Excel, I'll start this and I'll finish it. In Excel, Remember that to do a combination in Excel, you do equals COMBIN for combination. So equals COMBIN 3 comma 2. Okay, that's going to give us the combination of 3, choose 2. If you do that, you are going to get 3. This thing right here is 3. Why is it 3? Because that's how many ways there are to make 2 out of 3 free throws. So that first part of the formula is just saying how many ways can this happen? Whatever x is, how many ways can it happen? The next part is saying, okay, so we want 70%. We've got a 70% probability of making, and we want 2 makes, right? That's the number of successes. And then it's times 30%. Oops, these should be s's. And then times 30% to the power of 1, because that's the number of failures. Okay, so this is actually a very intuitive thing, and it did exactly what we did above. We took zero point 0.7 times 0.7 times 0.3. 0.7 times 0.7 is 0.7 squared times 0.3. That's exactly what this is. And then times the 3 for the 3 possible outcomes. Now, again, use Excel or Google Sheets or some other technology to do this. If you're using Excel or Google Sheets, you would type in equals combin 3, 3 comma 2. Multiplying in Excel is using the asterisk. So you're going to type in an asterisk, 0.7. Squaring or taking anything to a power, you're going to use the caret key that is above the 6. And then 2, so that's 0.7 squared. And then we need another asterisk, 0.3. So that's how you would type that into Excel to get that whole value. This whole thing then would give you the 0.44 that we got earlier. Okay? All right, wrapping this up then, let's talk about mean variance and standard deviation for a binomial random variable. Here's the good news. This is a whole lot easier than finding it for just any random variable. The mean for a binomial distribution, so mu sub x, is simply n times p. That's all it is. It's the number of trials times the probability of success. The variance is, again, I'll give you the symbols here, is n times p times 1 minus p. So again, basically taking your mean times the probability of failure. 1 minus p is the probability of failure. So then your standard deviation, of course, is just the square root of that. It's the square root of n times p times 1 minus p. Aren't those really just nice, simple, easy to use formulas? All right. So a company produces 200 televisions per day and estimates that 3% of these televisions are defective. Let X be the number of defective televisions. So there's our random variable. Find the mean and standard deviation. All right, so very simply, mean is 200 times the probability of success is 0.03. So notice here, right, success, we're calling it a defective television. So this is where we kind of flip it, right? And that's okay. But success is in this case counting how many defective televisions we get. We would expect to get 6 defective televisions out of 200. Makes complete sense, right? If 3% are defective, I would expect 3% of the 200 to be defective, or 6. All right, makes perfect sense. For standard deviation, it's the square root of, and I'm going to rewrite this, but it's really just 6, right? I'm going to rewrite the n times p, but we know that that's really just 6, and then times the probability of failure, 0.97, and then we take the square root of that, which is 5.82. Okay? So interpreting these, just to get one more look at interpreting, for the first one, for mean, we would say that for many TVs produced, we expect 6 out of every 200 to be defective. Okay. And then for standard deviation, the number of defective TVs, the number of defective TVs out of 200, and that's important, out of 200, typically varies by 5.82 TVs from the mean of 6. Okay. So that's how we'd interpret the mean and the standard deviation for those. So that's it for this lesson, random variables and binomial distribution out of chapter 6. And our next lesson, we'll be moving on then to chapter 7. I hope to see you then. Thank you very much.